Thank you, Professor De Hoogt. I'd now like to ask Bas Wols of KWR and Delft University of Technology to give his presentation. Bas Wols just finished a PhD on the topic of computational fluid dynamics in drinking water, and is also experience in ozonation, UV disinfection and UV oxidation. He is now working as a scientific researcher at KWR.
Thank you, Alex. So I will talk about the work we did on modeling of QSAR, a different model than Alex mentioned, where my PhD was about, and we want to use that to predict compound degradation by different water treatment processes. And I will show an example of a UV oxidation process. So you all know the relevance of emerging compounds. That's why you're probably in this room. So you also know that we like to remove those compounds. But usually we do not know that from the start, because those compounds can be very different. The chemical structure is very different, so how they react to the different water treatment processes can be very different. So the removal rate can range from 1% to 100%. So if you want to know that, you'd like to measure that, but that's of course quite expensive to measure all those compounds. But also, for some compounds, it's even not possible to measure that because the analytical techniques are not developed for that compound. So model predictions are also very interested to obtain how they are removed. And one of these techniques is QSAR, quantitative structure activity relationship, which relates the, as you see, this is, thank you. So a QSAR relates the chemical structure to a certain activity or property of the compound. And it's mostly used in pharmacologic, whatever, you see it. And it's used in toxicity to make predictions of new pharmaceuticals and also to predict how toxic compounds are before they are even developed or on the markets. So how it works, you know the chemical compound and you know the 3D structure of that compound, and from that structure you derive certain properties, or you characterize that compound by the descriptors, which we call descriptors. And that can be very different. So one of them is molecular weight, of course, very known, but it can also be quite exotic and quite difficult, which are related to the topology of the compounds, also related to the charges or the hydrophobicity. It can be all kinds of different properties of the compound. And you relate that in the end to the endpoints, so which you would like to know, which can be, for example, a biological activity, but also a property like a boiling point or something related to water treatment. And that's where we're interested in. So where can you use it for? You can use it for all kinds of different water treatment processes. I mentioned a few on this slide. And in this work, I focused on the UV advanced oxidation process, which is one of my expertise. But you can also use it for other processes. Well, I used a scheme to show how we developed it. I used two different schemes. This is the first one, and the other one will follow in the next slide. Because if you're looking at water treatment processes, there are also some other effects you need to account for. So one of them is the water matrix, with all the different compounds and all the background compounds which may compete with the target compound you're interested in how it is removed. And there are also different treatment processes with process conditions of that treatment process, and also different reactor configurations. So one approach is to put all the information from these three parts of the water treatment process together and put them as descriptors together and relate that descriptors directly to the removal of a compound. And you do that by statistical models. So the actual QSAR is then all the descriptors, including properties of the treatment process and the water matrix. And from that you directly predict the removal. But one of the disadvantages is this is kind of a black box, because there is no information from the real process or how the process works. It's not in this model. It's all related to the statistical part. In the other one, you use a process model to make prediction of the removal, and the input of that process model is, for example, for UV there is the reaction rate with hydroxyl radicals, and you use that as an input in the process model, and you develop the QSAR for that property, for example, the reaction rate with OH radicals. And the other effects of the process, for example, the water matrix, the background substances in the water, you put that in the process model, and also different reactor configurations, and so on. So in this way you develop your QSAR for a smaller part of the complete picture, but it's more focused on a property which is relevant for that type of treatment process. And in our case we focused on hydroxyl radical reactions, but it can, for other processes, it can of course be other properties. So we use a sort of progressive scheme to develop these QSARs, and I used 7 steps, and I will follow them with you, and I will show an example of UV advanced oxidation process for the reaction rate with hydroxyl radicals, to show what results we obtain from that QSAR approach. So first of all, we start with the selection of the endpoints. So that's the property we like to predict with the QSAR. So as I already mentioned, in this case this will be the hydroxyl radical reaction rate constant. And I came up with 153 compounds with known reaction rate constant from literature. Of course you can use measured data to obtain this, but for this hydroxyl radical reaction, which is quite known, there are quite some information in literature. So once you selected the endpoints, you go on to the next steps, and that is to obtain the descriptors. So the descriptors characterize the compound itself. So you have a 3D structure of a chemical, and you put that in different chemical modeling software. And from that you obtain all those descriptors. And in our case we had about 1,000 descriptors, which are quite a lot. But you should be a little careful, because some descriptors might represent the same aspect of the chemical compound. So you should check if they have not a big cross correlation. So, well, once you have the data, you have the descriptor data and the endpoint which you like to predict. There's also an important part of data splitting, because you would like to, you need a lot of compounds to train the statistical model to make the prediction, but you also like to validate that with other compounds. So you have to split the data in a certain part to train the QSAR model, and also the other part to validate the QSAR model. And we use a technique called self-organizing maps, because if we split the data, we like to have more or less the same, that represents the same part of compounds, that it's not very different. So that's why we use a technique of self-organizing maps, which more or less puts all the compounds in a figure, and they use all the descriptor data to map similar compounds together and dissimilar compounds far away. And I will show that in this picture. And this, well, these are all the compounds we use, so these are quite a lot. And if they are in the same node, then they are really closely related, which you can also see from the name of the compound in some cases. And if they are at the other part, they can be quite different. So, and then from this information we use some part of them for the training set, and another part for the test set, for the validation, and well, in such a way that it nicely covers the whole space. So I used quite a lot of compounds for the training, because we need a lot of compounds to train the QSAR, and we used some 26 compounds for the validation. So the next step is the training of the QSARs. Well, since I told that we got about 1,000 descriptors, but usually we only choose a few, and we want to choose the best ones. So we need to try that from the 1,000 we obtained. And therefore we need genetic algorithms, because you can have quite a lot of combinations from 5 out of 1,000. So you need genetic algorithms which quite fast can get good results. And we combine that with multiple linear regression techniques, which put a linear regression between the descriptor and the endpoint, the reaction rate of hydroxyl radicals. And I will show that after this slide for our test set, or for our example. And the fifth step is to do the external validation, which is often neglected, but I would like to stress that it's really important. As one of the famous QSAR Kubindi guy says, that the external validation is the real criteria to get a good result. And it's often neglected because there is not much data available, but you should really do that, because otherwise you can get a QSAR, but you don't know if it will work. So I used all the data for the UV advanced oxidation process for the hydroxyl radical rates. And here you can see different models I obtained from the genetic algorithms, which were supposed to be the best. So these are the, one is the best, and I got some different one, but they were listed from good to less good. And well, if you look at them, they look a bit exotic with all the names, because there are thousands, so they have a lot of names. But some of them are related to the charge of the compounds. That's the charge on the C atom. Some are related to the topology of the chemical structure, but some are related to the hydrophobicity, and some just indicate a certain group in the structure. So, for example, a CH3 group, or a OH group, or a carboxyl group. All those things can show up to be relevant for this OH radical reaction rates. So here you see for these the first model the different descriptors against the logarithmic of the hydroxyl radical rate constant, and they're all scaled between 0 and 1. And there you can see, well, you see some relations between them. And I should mention that the black dots are the training set, and the blue triangles are the test set. And you see some relation that it goes down and here it goes a little up, but it's not that easy to see. But if you combine that together, you get quite a nice relation. So you put the prediction against the observed values, and you see that they all fall within 5 or 10% of the predicted values for both the training and the test sets. So this QSAR looks, the prediction looks okay. But we want to know a little more about it. How does it work? So we also need a statistical interpretation of the model. So then you're going into the statistics, and you're looking at different statistical tests to check if the model is okay. Another one is cross-validation, where you leave one out of the training set, one compound, and you make a prediction for that one compound, and you do that for all. You repeat that for all compounds. Another one is permutation testing to check if there is no correlation by chance, which can be a problem because you use that so much data. You can have just a chance correlation which you want to remove out. And the last part is the applicability domain, which tells you if a chemical is applicable, if you look at the different descriptors, and they have a certain range, and if a new chemical is within that range or not. And I will show that with a plot later on. Well, here you see the different statistical parameters for the 5 QSAR models we obtained. And you see that the R squared is about 0.8 for the best one, which is quite okay. And I need to remove 5 outliers because they had too much difference. I will show that in another plot why I removed them. And you see that for the test set, the R squared is a little lower. So, well, it's still okay, but it's not that high. But if you look at the residual, so that's the difference between the prediction and the observation, you see that there in the test set they are also okay. So the R squared is not always that good visualization of the statistical performance. And if you look at the distribution of the residuals, well, you see that most are within a certain range, and some fall out a little. And, well, in the next step, we look at the applicability domain. Here you see the residuals, but then divided by the standard deviation of the complete part. And if that is higher than 2.1, it's considered as an outlier, because then that compound deviates too much from in the model. And the other one is the leverage, which is sort of influence which a compound has on the complete model. And if that influence is very high, then a prediction can also be unreliable, because then it may change the model too much. So if you have a new compound, it should have a not too high leverage, because it should not influence the model too much. And in the other part, it should, of course, not have too much residual, but sometimes you don't know because you want to predict that part. But this is more or less the space for which this QSAR is valid. So, well, with all these difficult statistical data, I will leave it from that. Hope you're still awake. But, oh, I forget one important part, which is the mechanistic interpretation. So you try to understand what really happens. So, what is responsible for that? And in our case, we've seen that the descriptors are related to the electronic charges, which can be quite logical, because the OH radical is a radical reaction with the compound, but also the structure and the structural features present to different parts of the chemical structure which are on the different groups on it can be of influence, but also the topological distribution of the compound. I will not. We're still looking at more details of that, but that's as far as I will tell you here. So we end with a conclusion that we're still working on the development of these QSARs for specifically the drinking water treatment processes. And I showed you the knowledge-based approach, where you calculate one certain property to use in a process model. The other one is the database, which is more a black box approach, which is less favorable to use, but if you don't know much about the process, you can still try that. So far we have promising results for the UV advanced oxidation, and in the future work we try to include more compounds and use other treatment processes, and also to make a classification of compounds, because in our case we developed a QSAR for all the compounds, which can be quite different, and you can also try to develop a few QSARs which more closely related chemicals. And that's it. Thank you for your attention.